Hi guys, this is Miss Cavic. Today we're going to be taking a look at a general view of kinematics. So a general overview of what you need to know for the AP Physics 1 exam kinematics. Keep watching. So our first topic is, what is kinematics? Kinematics tends to be a topic that is difficult for students, and I feel like that's because it's the first unit we do. So you're learning a lot about the language of physics while you learn physics. So let's start with the general definition of what is kinematics. And kinematics is the study of motion. I like to say without regard to the cause of the motion. So we know now, after studying a year of physics, that the cause of the motion is forces. So we're not looking at why the forces happen or why the motion happens in terms of the forces. We're basically looking at after the motion starts. So if you throw something, we're looking at after it leaves your hand and before it hits the ground. So these are some of our basic terms we're going to look at real quick for kinematics. So kinematics, number one, position. Position is referred to as x. And think about it as just where you are. So if you just have something like a line, and you're calling this 0, you might be 1 meter from that line. You might be 2 meters from that line. You might be 3 meters from that line. You might be on the other side. You might be -1 meters, whatever, where you are. Distance. I like to think about distance. We don't really have a symbol for distance. Sometimes we call that, sorry about that, sometimes we use a D for distance. I don't really like doing that. But for distance, just think about your actual steps that you took. So if you started at some position on Earth and you walked up here, and then you walked over here, and then you walked over here, and you ended, let's call that position 1 and position 2, and there. We would count your steps on how far you walked. Maybe that's measured in 10 meters, whatever. It's measured in meters usually, just how far you walked. So what is the difference between distance and displacement? Well, you started at 1 and you ended at 2. So you're really in a straight line distance only this far from where you started. So displacement is delta x. It is your change in position. And how do we measure position in physics? Or how do we refer to position in physics? Like, how do we measure, like, what unit? We would use meters. And then what symbol do we use for change? And for change, we always use delta. Delta x. So that's why this is delta. And what does delta mean? Delta means final minus initial. And I use an O for initial for not, like x naught is how I would say that. Some people or books or teachers might use an I, and that's totally fine too. So we would measure where we ended minus where we started. So here we would do x2 minus x1, and we would get delta x. So what is velocity? Well, the velocity is a v. We said these were all measured in meters, and velocity is the rate of change of your position. And sometimes you'll see that written as with respect to time. So we're looking at how your position changes over time. Velocity is measured in meters per second. And maybe you're familiar with using miles per hour. That also measures velocity. So it is the rate of change, how fast you are changing your velocity. A little different than speed. And a lot of times we want to think about speed as just your, your velocity without direction. because we'll look at how it's important that velocity and displacement have direction. But think about speed as being just like your just velocity. It doesn't matter what direction it's going in. It doesn't necessarily, think about it as being your distance. Just your change in distance. With respect to time. So our little like green path up here, for our velocity we would measure like this displacement over time. Or here we would look at how this green path changed over time. You can get two very different values for that, because if you're meandering around or if you're moving in a circle, you might get a different value for your speed and velocity, not just a different like direction, you know. They can be different. So for our acceleration, what is our acceleration? Well, acceleration is measured in A. Acceleration is also a rate of change. It is rate of change of velocity. With respect to time. So this is our meters per second, which we usually call meters per second squared. So these are basic kinematics vocabulary words. So let's look at signs of motion. Like, what does it mean if you have a positive velocity or a negative velocity, or a positive acceleration or a negative acceleration? So I like to do this lab at the very beginning of the school year, where we have this little motion detector. Detector, there you go, bad spelling. And we have this little cart we put on this track, and we measure the velocity and acceleration and position and all that stuff on this cart. So think about the motion detector itself being like our 0 position. If our object is moving away from the motion detector, we call that a positive velocity. We're moving away from our origin point. If our cart was moving back towards the motion detector, we call that a negative velocity. Now for position, generally we think of position being positive, but like position would be on generally the right side of the motion detector. This is positive position, and on the left side we have negative position. So same thing with our acceleration. We can have positive and negative acceleration, and we always want to think that positive means speeding up and negative means slowing down. That is not true. So let's think about if our velocity and acceleration are both positive, your object is speeding up. This would be our like general sense of you're moving away from this origin and the velocity is increasing. Let's say you had a velocity of 5 meters per second. You're adding 5 meters per second every second. So after 2 seconds, you're going 10 more meters per second. After 4 seconds, you would be going 20 more meters per second, and so on. If our velocity and acceleration are both negative, our object is also speeding up. So this would be like we are increasing our velocity towards the origin. And then what do you think about if our velocity is positive and our acceleration is negative? Or our velocity is positive, or our velocity is negative, acceleration is positive, or acceleration negative, velocity positive? Both of these cases, our object is slowing down. Let's graphically represent some of these terms with a motion graph. So with a motion graph, we're taking our motion and we're visually representing it. Generally, we look at position time, velocity time, and acceleration time. So I'm going to make 4 sets of graphs, and we're going to look at each of those 4 cases I drew up there. I'll do another one here. And I'll do one more down here. Alright, just so you know my axes, important our axes are labeled. Right, so I was a little busy, but we're going to look at each of these cases that we wrote about up here. Positive, negative, positive, negative, negative, positive, 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 negative, negative. Alright, so let's get really basic with our graph. What if our position was like this? Our position did not change, but our velocity or our time is changing. If your position is not changing, but time is changing, you have 0 velocity and 0 acceleration. What if you have this? You have a slope of a line, but the slope of that line is a single number. What is your velocity? Well, you're changing your position at a constant rate, you have a constant velocity, and then you also have 0 acceleration. Let's make it a little more interesting. What if your position changes like that? Well, let's look. The rate of change of this line increases, so our velocity increases, but our acceleration stays constant. So here we have a positive position, a negative velocity, and a positive position, a positive velocity, and a positive acceleration. So this object is speeding up. Let's look at a little way to kind of judge that without having to kind of think about the rate of change in each case. So I'm going to write position, velocity, acceleration. If you have a graph that is position versus time, and you want to read the velocity of that graph, or the velocity of that object, you're going to look at the slope of the line. So the slope of this line is positive and increasing, so our velocity is positive and increasing. If you have a velocity graph and you want to read acceleration, you also look at the slope of the line. The slope of this line is positive, and the rate of it is constant, so this acceleration is positive and the rate of it's constant. If you want to go the opposite way, if you want to look at acceleration graph and you want to figure out your object's velocity, you look at the area under the curve, and that area tells you the change in velocity, not the velocity at one point, but the velocity over that time interval. And likewise, if you have the velocity graph, you want to read position, you look at the area, and it tells you the change in your position, which we call displacement. So this will tell you how displaced your object is from the origin. I like to think about this little diagram anytime I'm analyzing motion graphs. Kind of helps me to write them in order X, V, A, and remember what I'm looking at. So this object had a positive position, positive velocity, positive acceleration. Let's look at a negative velocity, negative acceleration. I'm going to keep my position positive. So I want a velocity here that is negative. So I'm going to start with a positive velocity, and I'm going to make my velocity decrease. Well, this object is slowing down. It starts with a positive velocity, and that velocity decreases. So this is a positive velocity because it does start above the origin. So the slope of this line is negative. So our acceleration is going to be negative. This object is slowing down. What would the position graph of this look like? We need a positive slope of this line, but we need that slope to decrease. So we're going to start with a big slope and go to a smaller slope. This object is slowing down. Positive position, positive velocity, it's above the x-axis, then negative acceleration. Let's do a different case. Let's say our velocity was 0, but then went into the negative. Well, the slope of this line is negative. So we have a negative velocity and a negative acceleration. This object is speeding up. It might seem counterintuitive, but think about that velocity value is getting larger in the negative direction. So this object is speeding up. How can we draw that? Well, we need to start with no slope and then get to a bigger slope. And the slope of that line has to be negative. So we're going to start with no slope and get to a bigger slope. And my line has to curve down because my velocity is negative. So we have one more case to do. We're going to look at what happens if you have a, let's see, we did positive velocity, negative acceleration. Let's do negative velocity and positive acceleration. So what does that look like? I need my acceleration graph to be positive, but my velocity to be negative. How can I do that? I have to be on the negative side of the y-axis, and my line has to have a positive slope, so we're looking like this. This object starts with a negative velocity, and it gets closer to 0, so this object is slowing down. How would this look like on my position graph? I'm going to start with a negative velocity, and my slope is going to get smaller. How does that look? Well, let's think about what this one looked like, and think about it being the opposite. We start with a velocity, and that velocity decreases. Let's make that a little better. Something like that, where our slope is negative, but our slope is kind of decreasing. So there are our basic cases for motion graphs. And we'll have some cases, we'll look at cases where you have, y versus time instead of x versus time. That just means up and down instead of side to side, and we can do that too. So let's look at the kinematic equations, and I think that'll take us through this first video. So our kinematic equations are really important. A lot of times we learn this equation first, and I do not like this equation at all. I like looking at the kinematic equations kind of in their proper form. So I give the kinematic equations names. Our first equation is kind of the definition of acceleration. And our definition of acceleration, we said at the beginning of the video, was the rate of change of velocity with respect to time. So acceleration equals the change in velocity over time. Well, how do we write change in velocity? Well, change means final minus initial. And this equation is usually solved out for final velocity. So if we solve this equation for final velocity, we get final equals initial plus AT. This is equation 1. I call him Knox. This equation has no x, no displacement in it. And that's going to be important when we solve a problem. If we have a problem and we're looking for x, we're not going to use Knox. So number 2 is my personal favorite. Delta x equals v naught t plus 1/2 at squared. And I call him Nov. Nov has no VF in it. No final velocity. This one's great for a lot of projectile problems where you don't know how fast something's going at the end of its motion, only how fast it's going at the beginning of the motion. And then our third one I call not. And for some reason, not is usually one of my students' least favorite equations, but it's very convenient in a lot of kind of car problems. I don't know, we see this a lot with like a car skidding and we knew how far it skid, where you don't know the time. So if you are solving an equation and the equation tells, or solving a problem, and the problem tells you nothing about time, you probably going to use not. So there is a fourth kinematic equation. It is not on your equation sheet, but you are allowed to use it if you know it. Well, we have not, nov, and nox. We always have to know our initial velocity. You have to know where your object starts. The only thing you don't have to know is where your acceleration is. So our last equation is going to be NOAA. And you are allowed to use NOAA if you know NOAA, but NOAA is not on your equation sheet. So NOAA is delta x is 1/2 VF plus V naught times time. And if you know it, it has no acceleration. You got it. So this brings us to our 5 kinematics variables. Our 5 variables are delta x, initial velocity, displacement, initial velocity, final velocity, acceleration, time. You have to know 3 things to solve a problem. All of our equations have 4 variables in it. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All of our equations have 4 variables. And you can only have 1 unknown in an equation. So in a problem you're solving, you have to know 3 things to solve the problem. So when you solve a problem, make sure you write down your variables. Number 1 most important step, I like to what I call a K chart, where you list your variables and you fill in what you know. So you have a very simple problem where you're like, okay, I know, let's say we're doing a problem where it's like, we know maybe that an object travels 5 meters. It started with an initial velocity of 10 meters per second. It took that object 2 seconds to complete that motion. And then we want to know the acceleration of the object. There's always going to be one thing you don't care about. This is how you pick an equation. And a lot of times students see their equation sheet and see so many equations, they get confused. Use what you don't know, what you don't care about to pick your equation. So if I'm given displacement, velocity, time, I want acceleration, who am I going to use? Nov. I'm going to use him, and I can solve for the acceleration. So make sure when you solve a problem, always important you list your variables. So there is our first video on kind of a general overview. That was on kinematics. I feel like I forgot a lot of things on kinematics from this video, but I hope it was a helpful, very kind of general overview of what you need to know about kinematics for AP Physics 1. Thanks for watching.